Welcome back to Computer Lessons.
Data transmission and storage systems face physical limits from hardware capacity. Information theory provides mathematical tools to overcome these constraints through the science of data compression. This process identifies and removes redundant patterns from a raw bit stream to reduce the total storage footprint. The concept of entropy defines the minimum bits required to represent a specific piece of information. Claude Shannon established this foundation by proving that data contains inherent predictability based on symbol frequency. Understanding entropy allows engineers to design algorithms that reach theoretical limits of efficiency. Compression techniques divide into two distinct categories known as lossless and lossy architectures for various use cases. Lossless compression ensures that every single bit of the file remains intact after reconstruction. This method is mandatory for executable Codecs documents and critical system database files. The zip file format utilizes the DEFLATE algorithm, which combines two distinct mathematical strategies for maximum efficiency. It first identifies repeating sequences of bytes using a technique called LZ77. This hardware-level approach replaces duplicate data with a pointer to a previous occurrence of that string. The LZ77 algorithm operates by scanning the input stream for the longest matching sequence. Instead of storing literal data again, the system records a distance and a length value. This reduction strategy works best on files with high internal repetition, such as source code or logs. After the pointer substitution, the algorithm applies Huffman coding to the remaining values for further size reduction. Huffman coding assigns shorter bit sequences to frequent symbols and longer sequences to rare ones. This variable length encoding ensures that common characters consume the least amount of space. Building a Huffman tree requires a priority queue to determine the optimal binary representation for every data symbol. The most frequent symbols reside near the root of the tree for fast access and low bit counts. This prefix-free property prevents ambiguity during the decoding process at the hardware level. The DEFLATE standard remains the most used compression method due to its balance of speed and efficiency. It powers the PNG image format and the gzip protocol used to compress websites. Every byte saved during transmission reduces the load on network routers and data centers. Dictionary-based compression excels at text, but struggles with complex media like photographs or audio recordings. These files contain noise and variations that prevent the identification of exact repeating patterns in the bit stream. To address this challenge, engineers developed lossy compression, which accepts a controlled amount of loss. Lossy compression utilizes the limits of human biology to discard information that the brain cannot perceive. By removing imperceptible data, the algorithm achieves massive reductions in file size without apparent quality degradation. This trade-off is the reason we can stream high-definition video over standard wireless connections. The MP3 format revolutionized music by applying psychoacoustic models to the signal during the encoding. It identifies sounds that the human ear cannot hear due to the physical properties of the ear. These discarded frequencies allow the file to shrink to 10% of its original size. Frequency masking occurs when a loud sound at a specific frequency drowns out a quieter sound. The encoder calculates the masking threshold and removes the quiet signals that the brain would ignore. This process focuses bit allocation on audible portions of the spectrum to maintain quality. Temporal masking describes how a loud sound prevents the perception of quieter sounds that happen before or after. The brain requires a recovery period after a loud stimulus, which creates a window for data removal. Engineers exploit this biological delay to further compress the audio bit stream during complex passages. The fast Fourier transform, or FFT, serves as the engine for converting audio waves into frequency data. This transformation allows the encoder to analyze the signal in the frequency domain instead of the time domain. Manipulating frequencies is far more efficient for applying psychoacoustic masks and canned bit allocation strategies. Bitrate selection determines the balance between audio fidelity and the size of the compressed file. A higher bitrate provides more data for the mathematical model to preserve subtle nuances of the sound. Low bitrates introduce audible artifacts, where the compression process removes too much relevant information. Quantization is the process of mapping a large set of values to a smaller discrete set of numbers. This step introduces a controlled amount of noise known as quantization error into the final audio stream. Modern encoders use sophisticated noise shaping techniques to hide this error within audio. Image compression formats like JPEG utilize the Discrete Cosine Transform to group visual data into frequency blocks. The algorithm separates brightness information from color because the human eye is sensitive to intensity. Discarding fine color details allows for significant size reduction with minimal impact on visual perception. Video compression relies on the fact that most frames in a sequence are almost identical to the previous one. Instead of storing every pixel for every frame, the encoder records only the changes between them. This technique, known as inter-frame compression, is the backbone of modern video streaming services. Motion estimation algorithms track objects as they move across the screen to predict the content of future frames. The system stores a motion vector instead of a full image to describe the displacement of these pixels. This logic allows for high-definition playback at bitrates that were once considered impossible. Keyframes or iframes contain the complete image data and serve as the anchor points for the predictive frames. P frames and B frames then reference these keyframes to reconstruct the intermediate motion between the fixed points. This hierarchy ensures that the video stream remains stable despite the discarded data. Modern codecs like H.265 or AV1 use advanced mathematical models to improve compression efficiency by 50%. These standards require massive computational power to encode, but result in much smaller files for the consumer. Hardware acceleration inside GPUs handles this task to ensure smooth playback without draining power. Compression artifacts appear as blocks or blurs when the algorithm exceeds the limit of data removal for a bit stream. These visual glitches represent the failure of the mathematical model to correctly represent the original scene. Engineers constantly refine these models to push the boundaries of quality per bit. The bit stream itself is a structured sequence of headers, data packets, and error correction codes for transmission. Protocols like zip and MP3 include checksums to verify that the file remains intact after the decompression. Even a single-bit error in a compressed file can render the entire document unreadable. Real-time compression allows for low-latency communication during video calls and online gaming sessions. These algorithms prioritize speed over maximum efficiency to prevent lag during the encoding and decoding phases. This balance is critical for maintaining a seamless user experience in interactive digital environments. Cloud storage providers use a technique called deduplication to avoid storing the same file multiple times on their servers. By comparing the cryptographic hash of files, the system keeps only one physical copy for all users. This cross-file compression saves exabytes of space across massive data centers. Artificial intelligence is now driving the next generation of neural compression, where models learn the optimal representations. These neural codecs can reconstruct high-quality images from a tiny fraction of the data required by JPEG. This technology will define the future of low-bandwidth communication and virtual reality experiences. The ability to move massive amounts of data across networks depends on these hidden mathematical structures. In our next technical episode, we will dive into the architecture of computer networking and internet protocols. We will explain how these compressed packets find their way through the mesh of routers.
Every digital file you open is the result of a battle between mathematical precision and physical storage limits. Without compression, the modern internet would collapse under the weight of raw, uncompressed data streams. Do you prioritize the precision of lossless files or the convenient size of lossy formats? If you found this explanation helpful, please hit the like button and subscribe to Computer Lessons. Don't forget to click the bell icon so you don't miss our next class. Thanks for watching and keep learning.